Chapter 19. Ionic equilibria in aqueous systems. Many salts are highly soluble in water. An example is the sodium chloride, the table salt, which is very soluble in water. There are also some salts only slightly dissolve in water. An example is lead iodide, a yellow solid. When water is added into this test tube, lead iodide remains as a solid on the bottom. Very tiny amount of lead iodide goes into the solution, and you can see the color of the solution is almost colorless. However, even though the solubility is very small, whenever it dissolves, it ionizes into two ions, the lead ion and the iodide ion. So even though the solubility is small, there are two ions in the solution, and there's equilibrium between the solid, lead iodide, and the ions in the solution. And we can write a reaction as this. The lead iodide as a solid reactant goes into the solution, ionizes into the lead ion and iodide. Okay? And iodide has two here. And as usual, we can write reaction quotient, which is the product divided by reactant. In this case, reactant is a solid. And we know solid has concentration is constant. That means the reaction quotient only depends on the two ions, the concentration of the two ions, because the concentration of solid doesn't change. So we can introduce a new expression similar to reaction quotient, but only involves these two ions, and that is called the ion product. So ion product, so it's the product of these two ions, which is similar to the reaction quotient. Okay, the difference is ion product ignores the solid, the reactants, only involves the product, the ions. As we have shown in the last slide, if a solid is only slightly dissolved in water and ionized into cation and anion, the reaction quotient can be represented by QSP, the ion product expression, which is the product of the ions. As we know, when reaction reaches equilibrium, reaction quotient equals equilibrium constant. So for the slightly soluble solid, when the solution is saturated, the system is at equilibrium and the QSP becomes KSP. QSP represents the reaction quotient and the KSP represents equilibrium constant, which is called the solubility product constant. KSP value of a salt indicates how far the dissolution proceeds at equilibrium, just like equilibrium constant measures how far the reaction proceeds at equilibrium. For example, if K is large, that means the reaction favors product. Similarly, if KSP is large, that means there's a lot of ions in the solution, so the solid is highly soluble. On the other hand, if KSP is very small, that means in the solution there's only tiny amount of ions, and so that indicates the solid is only slightly soluble. Sample problem 19.5. Write the ion product expression at equilibrium for each compound. Note that it says at equilibrium. So that means the reaction already saturated. Instead of write QSP, we should write KSP at equilibrium. Okay. Now also, sulfide is quite special, so we'll talk about D later. But first, let's look at A, B, C. So for A, magnesium carbonate. So we write reaction, magnesium carbonate, ionize, okay, solid, ionize into two ions, magnesium 2+, carbonate 2-. So remember, Ksp is similar to equilibrium constant, but ignore the reactants because it's a solid. And so in this case will be magnesium 2+ times carbonate 2-. Okay, next one, iron hydroxide. So here is iron hydroxide. Ionize into iron 2+ hydroxide minus, you need 2 of them. So the Ksp will be the iron 2+ times hydroxide squared. Okay, remember you have 2 here. Okay, next one, calcium phosphate. So calcium, here is calcium phosphate. Remember, calcium is 2+, phosphate is 3-, and therefore you need 2 phosphate. You need 3 carbonate of calcium. So you have 3 calcium, 2 phosphate, and therefore the Ksp will be calcium to the 3rd power, phosphate to the 2nd power. Question D involves silver sulfide. In general, metal sulfides behave very different from many other slightly soluble ionic compounds. This is because sulfide ion is strongly basic. Let's take manganese sulfide as example. So manganese sulfide only slightly soluble in water, and it ionizes into manganese ion and sulfide ion. Now sulfide ion hydrolyzes because it's basic. It hydrolyzes back into the weak acid, hydrogen sulfide. So react with water, hydrogen sulfide plus hydroxide. So this makes the solution basic. All right, and then the net reaction, you cancel the sulfide, and you get manganese sulfide plus water forms manganese ion plus hydrogen sulfide plus hydroxide ion. Okay, so what is Ksp? So the net, this is the net reaction when manganese sulfide slightly dissolved in water, and the Ksp should be involves only these 3 products. So that's manganese ion, hydrogen sulfide, and hydroxide. Okay, so whenever we deal with a metal sulfide, we can think of the dissolution of the metal sulfide as a 2-step process. Now let's look at D, silver sulfide. And we think about this as a 2-step process. The first step, silver sulfide ionize into silver ion and sulfide ion. And then sulfide ion hydrolyze to hydrogen sulfide and hydroxide. And then we write the net reaction. We cancel sulfide ion and give you the net reaction. Silver sulfide plus water goes to 2 silver ion, hydrogen sulfide, hydroxide. And then we write Ksp, which is the product of the ions, silver to the 2nd power, hydrogen sulfide, and hydroxide. This table shows solubility product constant of selected ionic compounds. Silver sulfide, for example, Ksp is 8 × 10⁻⁴, and this is a very small number indicating silver sulfide is very insoluble in water. Lead sulfate has a Ksp 1.6 × 10⁻⁸. So lead sulfate is much more soluble than silver sulfide. And zinc iodate, Ksp 3.9 × 10⁻⁶. So this is the highest solubility among all these solids. Sample problem 19.6. Lead sulfate is a key component in lead acid car batteries. Its solubility in water is this amount. What is the Ksp of lead sulfate? To calculate the Ksp, we need the concentration of the ions. In this case, will be the lead ion and the sulfate ion. So we need the concentration. And how do we find the concentration? Okay, here give us the solubility. No matter how many grams we add into water, this is the only amount that can dissolve. So for example, you may add 100 gram or even 1000 gram of lead sulfate, but only 4.25 times 10 to the minus 3 gram will dissolve in 100 milliliter. That's the solubility. So using this amount, we can calculate how many grams lead ion, how many grams sulfate ion in the solution. And then we can calculate the molarity concentration. So we calculate the moles of each one, okay, grams, calculate the moles, and then we calculate the molarity, and then we calculate the KSP. In question B, when lead fluoride is shaken with pure water, the solubility is found to be 0.64 gram per liter. Calculate KSP. Now this question is similar to A. We need to convert solubility gram per liter to mole per liter first, all right? And then using the dissolution reaction to find lead concentration, fluoride concentration, and then we can calculate KSP. So here is the dissolution reaction. Note that every salt forms 2 fluoride, and so KSP should be squared, fluoride squared, okay? And here is how we convert concentration from grams per liter to moles per liter. So we divide by molar mass. And so when we divide the molar mass, the gram cancel, and we get moles per liter, and that's the molarity. Okay, combine the numbers, give you 2.6 times 10 to the minus 3. Now to calculate the ion concentration, we look at the dissolution reaction. We find that the concentration of lead should equal to the concentration of the salt goes into the solution. So these are the same. And fluoride should be twice of this amount, times 2. Okay, because every salt becomes 2 fluoride. All right. So here are the concentration of lead, and this is the concentration of fluoride. And when we write the KSP, don't forget the square here. Okay, whenever you have coefficient 2, you need to square fluoride. So this is the KSP, and the lead concentration, fluoride, square it, and that's the final answer, KSP, 7 times 10 to the minus 8. Sample problem 19.7. This question asks you to calculate the molar solubility of calcium hydroxide in water if KSP is given. So compare with last question. In the last question, we know the solubility and to calculate the KSP, which is straightforward. In this question, we know KSP, we want to calculate the solubility. So in this kind of question, we need to set up the reaction table, the dissolution reaction, and set up the reaction table, and we assume the solubility is an unknown, for example, S. And then we express the concentration of the 2 ions as a function of S, and then write KSP to solve S. To write the reaction table, we first write the dissolution reaction. Calcium hydroxide forms calcium ion and the 2 hydroxide ion. Initial concentration, the ions are all 0, and note that we do not put anything under calcium hydroxide because it's a solid, which does not contribute to KSP. And to write the change, we assume the solubility is S, just like we use X as an unknown. Here we use S to represent the solubility. Solubility means that's the amount of solid that goes into the solution, and we assume all going to the solution becomes ions. So the cation calcium is just the solubility, but the hydroxide is twice of it. Okay, because whenever you have 1 mole of calcium hydroxide into the solution, it becomes 2 moles of hydroxide. So you have 2 times S. And therefore, at equilibrium, calcium ion is S. So all the solid going into the solution becomes 1 calcium ion and 2 S hydroxide ion. And from this table, okay, we know the concentration of the ions. We can calculate the Ksp. So Ksp should be S times 2s to the squared. So 2s squared and s. And that gives you 4 times s to the third power. Okay. So note that 2s combined together square should be 4s squared. All right. And 4s squared times s, that's 4s cubed. All right. And the Ksp is given. So from this equation, we can solve S. All right. So we move 4 to the right side. So S cubed equals the solubility divided by 4. And therefore, S can be calculated is the cube root. All right. And that is 1.2 times 10 to the minus 2 molarity. So that's the solubility. This table shows the relationship between Ksp and the solubility. So compare lead sulfate and barium chromate. Lead sulfate Ksp 10 to the minus 8, which is greater than the Ksp of barium chromate 10 to the minus 10. And the solubility of lead sulfate is higher than barium chromate. So the higher the Ksp, the greater the solubility. Note that these two salts both give you 2 ions. Lead sulfate gives lead ion and sulfate ion. Barium chromate gives barium 2 plus and chromate 2 minus. So both produce 2 ions. Now, if we compare barium chromate with silver chromate, okay, you can see although silver chromate Ksp is smaller, 10 to the minus 12, okay, than barium chromate, but the solubility is actually greater. Solubility for silver chromate is 8.7 times 10 to the minus 5 compared to 1.4. And this is because silver chromate generates 3 ions instead of 2. Okay, 2 of the silver ion and 1 chromate. So that's 2 ions. Each salt gives 3 ions. And therefore, when you compare Ksp solubility, you should compare only those have the same number of ions. And so then the higher the Ksp, the higher the solubility. This diagram shows the saturated lead chromate solution. Lead chromate is only slightly soluble, and so most of the solid remains on the bottom, and very small amount goes into the solution and produce lead ion and chromate ion. Now what happens if we add sodium chromate? Sodium chromate is highly soluble. Its ion produces sodium ion and chromate ion. Now because it's highly soluble, so almost all the salt becomes the ions. For example, if we add 0.3 molarity of the salt, then you will produce 0.3 molarity of chromate ion. Note that chromate ion is a common ion because it belongs not only to the sodium chromate but also to the lead chromate. Now, when we add the sodium chromate in the solution, it produces a lot of chromate ion. And because chromate ion is a product for this dissolution reaction, according to the Chatelier principle, when we add the product, the reaction goes reverse. And that will decrease the solubility. All right, so as you can see in this diagram, more solids start to come out of the solution because the reaction decrease solubility go to the left side. And this is called the common ion effect. When in a slightly soluble solid solution, if you add a salt, highly soluble salt that contains the common ion, that will decrease the solubility. Sample problem 19.8. In sample problem 19.7, we calculate the solubility of calcium hydroxide in water. Remember, we used the KSP and we set up a reaction table and assume solubility is S, and we solve the solubility, and the answer was 1.2 times 10 to the minus 2. Okay, so that's the solubility we solved in 19.7 for calcium hydroxide. Now, in this question, it asks you, what is the solubility if we have 0.1 molarity calcium nitrate added into the solution? And as we learned in the last slide, and this is to investigate the common ion effect, because calcium nitrate is a highly soluble salt which produces calcium, and calcium is a common ion because calcium hydroxide and calcium nitrate both has calcium. When we add a common ion, the reaction will go reverse and decrease solubility. So we would expect the solubility will be less than 1.2 times 10 to the minus 2. So how do we solve it? Well, the method is the same. Okay, we set up the reaction table. Okay, reaction table assume the solubility is S. The only difference is the initial concentration of the calcium. Calcium initial concentration now is not 0, but you need to add this amount due to the calcium nitrate. To write the reaction table, we first write a dissolution reaction. Calcium hydroxide produce calcium ion and 2 hydroxide ion. Now to write the initial concentration of calcium, we need to find out how much calcium produced by calcium nitrate. Now calcium nitrate is highly soluble, so if we have 0.1 molarity of calcium nitrate, it will produce 0.1 molarity of calcium ion. Okay, now you may ask, what kind of salts is highly soluble? Well, in chapter 4, there's a solubility rule, and you need to go over those rules. For example, group 1, cations, lithium, sodium, potassium. So group 1 cation or ammonium cation. So any salt containing these cations are highly soluble. Or the anions such as nitrate, okay, nitrate ion or perchlorate. Okay, salts containing these anions are highly soluble. Now, there are other rules, so you need to go over. But this salt is nitrate anion, contains nitrate, so it's a highly soluble salt. And it produces common ion calcium. Okay, and so now we can write the initial concentration. So calcium is 0.1, hydroxide is still 0, all right? And if we assume the solubility is unknown S, then we have calcium S, hydroxide is 2S, okay? And at equilibrium, then calcium is 0.1 plus S, hydroxide is still 2S. And then we write KSP. So KSP should be 2S squared. Note you have 2. 2S squared times 0.1 plus S. Okay, so here, if we assume solubility is very small, okay, and then 0.1 plus S can be approximated by just 0.1. and then 2s squared becomes 4s squared. Okay, 2s squared equals 4s squared. And this equals the k constant, which is 6.5 times 10 to the 6. Rearrange, we can calculate s. So here, 4s squared equals 6.1 times 10 to the minus 6 divided by 0.1 goes to the left side. So you get this one. All right, and then you can calculate s, and the solubility is 4 times 10 to the minus 3. Okay, compared to the solubility before you add the common ion, and you can see it becomes smaller. So it's consistent with our prediction that the common ion effect decrease solubility. Now also we need to check our assumption. So we write the calculated number divided by initial concentration, which is 4%, less than 5. So assumption is correct, and we can omit in this equation s and just write 0.1. Sometimes changes in pH value also affect the solubility of some slightly soluble ionic compounds. Now this only happens for those salts that contain anions of weak acids. For example, calcium carbonate produces calcium ion and carbonate ion. Carbonate ion come from weak acid bicarbonate. And the bicarbonate comes from another weak acid, carbonic acid. So if hydronium ion is added, hydronium ion will react with carbonate to go back to bicarbonate, and the bicarbonate go back to carbonic acid. And here are the two reactions. So you can see carbonate react with hydronium ion, go back to the weak acid bicarbonate. Bicarbonate react with hydronium ion, go back to the carbonic acids. Now note that carbonate is a product for this dissolution reaction. When hydronium ion is added, hydronium ion react with the product, so it removes the product. And according to the Chatelier principle, when product is removed, the reaction goes forward. That will increase the solubility, so more calcium carbonate will dissolve. So the net effect of adding hydronium ion is the removal of the carbonate anion, which causes an equilibrium shift to the right, so more calcium carbonate will dissolve. Now compare with the common ion effect. Common ion effect add product. The common ion is the product. So when add the product reaction go left side, decrease the solubility. On the other hand, adding hydronium ion remove the product and increase the solubility. Sample problem 19.9. Write balanced equation to explain whether addition of hydronium ion from a strong acid affects the solubility of each ionic compound. So in A, lead bromide, first we write the dissolution reaction, which produce lead ion and bromide ion. So the question is, does this anion react with hydronium ion added to the solution? If it doesn't, then it doesn't affect the solubility. Now, hydrogen bromide comes from a strong acid. Okay, so that means it won't go back. Because it's strong, so it actually produces bromide and hydronium ion instead of going backwards. And therefore, there's no reaction between bromide ion and hydronium ion. So the addition of strong acid has no effect on its solubility. Now let's look at B, copper hydroxide. So the dissolution reaction produces copper ion and hydroxide ion. So again, the question is, does hydronium ion react with hydroxide ion? Well, although it doesn't, hydroxide does not come from a weak acid, it does react with hydronium ion to form water, and that's the reaction. So because it forms water with hydronium ion, so adding hydronium ion remove hydroxide, remove product, reaction go forward, and therefore increase the solubility of copper hydroxide. Question C is iron sulfide, and the dissolution reaction is iron sulfide forms iron and sulfide ion. Now sulfide ion comes from a weak acid hydrogen sulfide ion, and this is quite a strong base, so it will react with hydronium ion and go back to the hydrogen sulfide, and therefore it will remove product and increase the solubility. Similar to reaction quotient and equilibrium constant, we can also use QSP and KSP to predict the formation of a precipitate. For example, when QSP equals KSP, that means the reaction is in equilibrium, or the solution is saturated. So the solid and the ions are in equilibrium. No change will occur. When QSP is greater than KSP, okay, that means there are more ions in the solution than saturated solution, because Q is the product of the ions. So a large Q means more product, more ions in the solution, and therefore the reaction will go reverse, go to the left to generate the solids, and the precipitate will form. On the other hand, if Q is less than K, okay, that means there are less ions in the solution than saturated solution. So more solid will dissolve and no precipitate will form. Instead, if you have solid, it will dissolve. Sample problem 19.10. A common laboratory method for preparing a precipitate is to mix solutions containing the component ions. Does a precipitate form when 0.1 liter of 0.3 molarity calcium nitrate is mixed with 0.2 liter of 0.06 molarity of sodium fluoride? Okay, so we mix two salts. One is sodium fluoride, the other is calcium nitrate, and we want to know if they form precipitate. But first we need to know how many ions, okay, what are the ions in the solution, okay? So calcium nitrate generate calcium ion, nitrate ion, and the sodium fluoride generate sodium ion and the fluoride ion. So in the solution of this mixture, we may have 4 different types of ions. The question is, do they combine to form precipitate? So we combine cation and anion. So first we can remove some of the highly soluble salts. For example, we know nitrate ion are always soluble. Okay, so anything combined with nitrate are very soluble. We don't need to consider this to form precipitate. And the sodium ion is a group 1 cation, so any anion combined with sodium also highly soluble, won't generate precipitate. So we can immediately remove these 2 ions. So the only possibility is calcium and fluoride, and these 2 may combine and form a precipitate. And the reaction would be calcium fluoride. If they form solid, it may forms ions, calcium ion and fluoride ion. The KSP for this ion, the dissolution reaction is calcium ion fluoride ion squared. Okay, so the plan is we need to calculate QSP. Okay, using this concentration, we calculate the concentration of calcium concentration, fluoride concentration to calculate the KSP. Compare with QSP, compare with KSP found from textbook. All right, if QSP is greater than KSP, that means there are more ions than saturated solution, so it will precipitate. We now calculate the ion concentration in order to calculate the QSP, and note that KSP already found from textbook. To calculate the concentrations of cation and anion, we notice that when we mix two liquids, the volume change. So 0.1 liter of calcium nitrate, 0.2 liter of sodium fluoride. So the total volume becomes 0.3 liter. And therefore, the concentration should be the moles divided by the new volume. So for calcium, we use the molarity times volume. Okay, so that's the number of moles divided by the new volume will be 0.1 plus 0.2. So the concentration of calcium in the solution of the mixture is 0.1 molarity. Similarly, to calculate the concentration of fluoride, we first calculate the number of moles added, and that will be 0.06 molarity times 0.2 volume, give you 0.012 moles, divided by the total volume, and that gives you the concentration. So now we can calculate the QSP in the solution, and the QSP is calcium times fluoride squared. Don't forget the square here. Okay, so that's the QSP. Compared to KSP, you can see Q is greater than K. So that means there are too many ions than saturated solution, and therefore precipitate will form. Sometimes we have a mixture of ions and we can separate them by selective precipitation. For example, when we have a mixture of copper ion and a magnesium ion, we can separate these two ions by adding hydroxide. And this is because hydroxide and the copper ion forms copper hydroxide, which has a KSP around 10 to the minus 20, very small. Hydroxide magnesium also form a solid with KSP around 10 to the minus 10. And so KSP1 is much smaller, means copper hydroxide is much more insoluble than magnesium hydroxide. So if we add enough amount of hydroxide so that the QSP for the magnesium hydroxide is close to KSP, so almost equal to KSP, that means it's about to precipitate, but not yet. And that will provide enough hydroxide to precipitate copper ion, because it forms copper hydroxide. The QSP for copper hydroxide is close to 10 to the minus 10, which is much greater than KSP for the copper hydroxide. So copper hydroxide will almost all precipitate, but magnesium hydroxide not yet. So in this way, magnesium stays in the solution, copper ion is precipitated. So we add a precipitating ion, in this case is the hydroxide ion, to the solution until QSP of the more soluble compound is almost equal to its KSP. So this is about magnesium hydroxide. It's more soluble, and we add enough hydroxide, so QSP is almost equal to its KSP, but not yet. So enough hydroxide, and the less soluble compound will precipitate in as large quantity as possible. Okay, because you have a lot of hydroxide, all right, and leaving behind the ion of more soluble compound. Sample problem 19.12, and this is an example of selective precipitation. A solution consists of 0.2 molarity magnesium chloride, 0.1 molarity copper chloride. And so in the solution, we have magnesium ion and the copper ion. The question is, how much hydroxide concentration is needed to separate these two metal ions. So Ksp are given. So one is 10 to the negative 10, and one is 10 to the negative 20. So apparently, copper hydroxide is less soluble than magnesium hydroxide. So if we add hydroxide, we expect copper hydroxide to precipitate first. As we showed in the last slide, the maximum hydroxide is the amount that make magnesium hydroxide QSP approximate equal to its KSP, and that's the maximum hydroxide you can add. Otherwise, both will precipitate. Okay, so first let's calculate the write the dissolution reaction. So this is magnesium hydroxide, and this is copper hydroxide. So the KSP, both metal ion times hydroxide squared. Okay, and now we assume we add hydroxide so that the QSP is about this number. Okay, that's the maximum hydroxide you can add. From this equation, then we can calculate hydroxide concentration, because magnesium concentration is given to be 0.2. Okay, 0.2 molarity magnesium chloride. So in the solution, you have magnesium concentration 0.2, and QS2 is equal to KSP because we want to be approximately equal. So a little bit less, and that's the maximum hydroxide. So let's let them equal to calculate maximum hydroxide. So hydroxide should be square root KSP divided by magnesium. So from this equation you can see hydroxide equals KSP divided by magnesium, and because you have a square, so you need to square root of it. Okay, so that's KSP, that's the magnesium concentration, and give you hydroxide concentration, and this is the maximum concentration you can add, because if you add a little bit more than this, then magnesium will precipitate also. So both ions will be precipitated, and so you cannot separate them. All right, but if you add hydroxide a little bit less than this one, then magnesium is still staying in the solution because QSP is still smaller, slightly smaller than KSP. So magnesium stays in solution, but the copper ion should already precipitate it, because KSP for copper hydroxide is much less. All right, so the QSP should be much greater than this already, because you can see QSP is close to 10 to the minus 10, so much greater than this. So to confirm this, let's calculate how much copper ions still in the solution, and so we can see if it precipitated. So to calculate the copper ion in the solution, and because now solid already come out, so the solution should be saturated. So Q should equal to K. All right, and therefore we can calculate Q by KSP equals copper ion times hydroxide squared. Okay, because the solution copper ion hydroxide are in equilibrium with solid, are in equilibrium with KSP. So KSP divided by hydroxide, and that gives you 7 times 10 to the minus 12, and that is a very small number. In the solution, you only have this small amount of copper ion left. Okay, remember we start with 0.1 molarity of copper ion, and now only this small amount left. So almost all copper ions are precipitated. Many metal ions can covalently bond to 2 or more anions or molecules called complex ions. For example, chromium can bond to 6 ammonium molecules to form complex ion. Here, ammonia is called a ligand. As we already know, many metals can bond to 2 or more water molecules to form metal hydrates. For example, aluminum can bond to 6 water molecules to form aluminum hexahydrate. So metal hydrates is also an example of a complex ion. When a metal hydrate, such as this one, is treated with ammonium molecule, usually the water around the metal ion may be replaced by ammonium molecule to form metal ammonium complex. And this reaction may complete in several steps at the molecular level. So first, one ammonia replace one water, and then second ammonia replace a second water, and the third and fourth. So all of them, all of the water molecules will be replaced. Now, for the overall reaction, we can write the equilibrium constant. But since the product has a liquid water, if we omit the water, then we get a new constant called formation constant. So the formation constant is the product, but not include water, divided by the reactants. Okay, the product is the ammonium complex. The reactant is the hydrate, metal hydrate. And therefore, Kf is a measure of the ability of the ligand to replace water, the ability to replace water. So the larger the Kf, the more the reaction goes to the metal complex of the ligand. The smaller means the reaction may favor the metal hydrate. This table shows the formation constants of some complex ions. Since most of these Kf are very high value, that means these ions, cyanide, ammonia, fluoride, hydroxide, they are ready to replace water from the metal hydrates to form these complex ions. Sample problem 1913. An industrial chemist converts zinc tetrahydrate to more stable zinc tetraammonium complex by mixing 50 liter 0.002 molarity of zinc hydrate and 25 liter 0.15 ammonia. What is the final zinc hydrate at equilibrium? So first, let's write the reaction to replace water by ammonia. So here is the reaction: zinc hydrate, 4 ammonia to replace 4 water to make the zinc ammonium complex. So write this reaction, and the Kf of the formation of this complex is given. So formation Kf should be the product omit water. So product divided by reactants. Okay. Now what it asks you is at equilibrium, what's the concentration? Okay. So to calculate the equilibrium concentration, we know we need to list a reaction table. We need to know the initial concentration, and we assume the change, and so we can solve the change using Kf, and then we can calculate equilibrium constant. But do we have initial concentration? Well, we have the molarity for zinc, all right, before we mix, okay? However, when we mix two liquids, the volume change, and therefore the initial concentration is not exactly 0.002. Instead, we need to use number of moles divided by the new volume to calculate the initial concentration first. So let's calculate first zinc hydrate initial concentration. So we add 50 liter and 0.002 molarity. That gives you number of moles, and then divide by the total volume when we mix two liquids together with ammonia. Okay, so that gives you the molarity of zinc ion or zinc hydrates. Okay, and the ammonia added is 25 liter and 0.15 molarity, but the volume also change, so we need to divide by new volume. So that's the initial concentration of ammonia after we mix together. So now we are ready to list the reaction table and solve X. Now let's list the reaction table. So here is the reaction. The zinc hydrate react with ammonia to form zinc ammonium complex, and water, and the initial concentration just calculated, and zinc ammonium complex is 0 at the beginning. Okay, now the next step is the change. So usually we'll say the reactance is -x, -4x, and x, right? And then we write the equilibrium and we use Kf to solve x. Now you can do that, but it's a lot of work. In this case, we don't have to do this. We have a better way, a simple way. Okay, so the reason is that the Kf in this case is huge. The Kf is about 10 to the 8th power. Such a large K means almost all the reactants are consumed. Okay? At least one of them is completely consumed. So which one? Well, we'll compare these two concentrations. Okay, one is 10 to the -3, okay, which is much smaller than the other one, 10 to the -2. Even if we times 4, because there's a coefficient of 4, we still get a number smaller than 5 times 10 to the -2. And that indicates zinc hydrate is the limiting reagent. So it's this one will almost consumed, all right? Almost consumed. So the change, you don't have to write x. Instead, you just approximate. That's all, almost all is consumed, okay? And the ammonia is 4 times the initial zinc hydrate, almost all consumed. And product is 1.3 times 10 to the -3. So in this way, you don't need to solve this x. However, at the equilibrium, usually we'll write initial minus this change. But because we approximate equal, so then this will be 0. But that's what we want to calculate, even though we know it's a small number, because they are very close. So it's close to 0, but not exactly. And this is what we want to calculate. And therefore, we have to solve it. So we assume this is the x. Okay, so we assume this is x because this is what we want to calculate, even though this is close to 0. But still, we want to find out exactly what is it. And so we let this to be 0, but the others we approximate. That's about all consumed for the metal hydrate. So 5 minus 4 times this one. So that gives you 4 times 5 times 10 to the -2. And that's the equilibrium concentration for ammonia at equilibrium, approximate. And this is approximate product at equilibrium. But this one, we cannot approximate to be 0. Okay, we have to find out. And so we write x. And then we write Kf. So Kf will be the product. In this case, it's 1.3 times 10 to the -3 divided by x divided by 4.5 times 10 to the second -2. Don't forget there's a 4 here. So it's 4 raised to power 4. Okay, and that equals Kf. And we can easily solve this x. So x can be solved to be 4.1 times 10 to the -7. And you can see this is a very small number, close to 0. But still, we have to solve it instead of say it's 0. Sample problem 19.14. This question asks you to calculate the solubility of silver bromide in water and be in 1.0 molarity hypo. Hypo is this molecule, sodium thiosulfate. Okay, so let's look at A in water. So it's a typical question about solubility of a salt. Okay, to do that, first let's write the dissolution reaction. Silver bromide, okay, in water. So small amount of silver bromide goes into water and becomes 2 ions. Okay, so there's a equilibrium between the solid and the ions, and Ksp is the product of the 2 ions. To calculate the solubility, we assume it is S. Solubility is S, and this is the amount of silver bromide that goes into the solution and becomes the 2 ions. So the silver ion will be S, bromide will also be S, and therefore the S squared, these two multiply together, is this Ksp. So S squared So S squared is KSP, and therefore we can easily calculate the S to be square root of this KSP. So the answer is 7.1 times 10 to the minus 7. In question B, it's about solubility in hypo. Hypo is sodium thiosulfate, and this also produce two ions, sodium ion and thiosulfate ion. Thiosulfate ion will combine with silver to form silver thiosulfate. So this question is more complicated than A. We need to consider all the reactions, all the possible reactions. So let's write the possible reaction. So first we have silver bromide. Okay, so the silver bromide produce silver ion and bromide ion. And when we add sodium thiosulfate, you have sodium ion which doesn't participate in the reaction, but the thiosulfate will combine with silver. So this comes from this one, sodium thiosulfate, but it will combine with silver to form silver thiosulfate. The KSP is given here. Okay, so that's the two possible reactions, and we can combine them into one reaction. Now, silver is the product in the first reaction, but a reactant in the second reaction, so we cancel it, and this is the overall reaction. Okay, so when you add the silver bromide in the sodium thiosulfate, and this will be the overall reaction. But what is the Kf for this reaction? Well, we know this one, we just calculated in A, and this one is given here. Okay, so this one should be the product of these two, because this reaction is the sum of these two. So the equilibrium constant should be the product of these two, and that gives you 24. All right, so we have a overall reaction in the solution. We have the K constant in the solution. So now we can list a reaction table and find the solubility in this solution. So here is the overall reaction, and the initial concentration is given for sodium thiosulfate is 1.0, and if we assume the solubility is S, and this is the amount goes into the solution to react with thiosulfate, and so that will be negative 2S, and the product is S and S, and the equilibrium concentration will be 1 minus 2S. Okay, so we can write the Kf should equals to S times S divided by 1.0 minus 2S, and that gives you 24, which we calculated in the last slide. Okay, and this equation can be easily solved, and in this case we can square root both sides, and so the left side will be S1 minus 2S, the right side is again square root 24. Okay, and square root 24 is 4.9. Okay, so we have this equation. So let me oops. Okay, so here S minus divided by 1 divided by 2S equals 4.9. So we can rearrange S equals 4.9 times 1 minus 2S, which equals 4.9 minus 9.8S. And let's move this to the left side. So S plus 9.8S equals 4.9. So that gives you 10.8S equals 4.9. So S equals 4.9 divided by 10.8. And the answer will be 0.45. And that's the solubility in sodium thiosulfate.